Today we are going to talk about a new method of integration that is called integrating by parts. Now, when I taught you about U substitution, I mentioned that U substitution undid which type of derivative? Do you remember? Chain. It undid the chain rule. Integration by parts is the process of undoing the product rule. So that's what we're learning how to do today. We are undoing the product rule. Now, this is a very long packet. We're not going to do every problem in it just due to time. And so we're going to skip around and do critical points to make sure that we cover everything we need to cover. Now, this first box right here is a list of all of the rules that we have learned that apply to A-B types of integrals. This is pretty much the same thing as you would see on your flip chart. All of these down here and the two that we added over here are the inverse trig functions, okay? So this is just a review and a good reference to have as you do your homework once we get to that point. Now, we have to find a corresponding way to undo the product rule. And here is the product rule, U times V prime plus V times U prime. Did we do it with U's and V's on the flip chart, or did we use F's and G's? I don't remember. What did we do? Let me look. Derivative rules. I think we did it with, no, we did it with U's and V's. We did do it with U's and V's. But anyway, this is going to be a procedure that takes the product rule and goes backwards. Now, what I want to do now is just focus on this box right here on your paper. Everybody look at this box. One of the skills you have to have as a college math student is the ability to look at a problem that is written in text and understand how they move from step to step to step, okay? Instead of you necessarily writing it down or the teacher explaining how the steps go. So here's what we're doing. We're taking this product right there, y equals U times V. Do you understand how this turns into the first line in the box? Does that make sense to you?
Yes.
Yes?
Wait, is it like a line? Like when being multiplied, you change it to addition?
No, yes, it kind of is. The product rule has always been this way. 1d2 plus 2d1. That's what this is. This is 1d2, this is 2, and d1. Do you remember 1d2 and 2d1?
Uh-huh.
It's been a while. Okay. Now, do you understand how they got from step 1 to step 2? It tells you out to the side. They don't always do that in college books. A lot of times they don't. They tell you out to the side that they multiply both sides by the dx and just have an equation that has dy's, because that looks more like integrals. Okay? On the next step, they integrated both sides. Now, we've never done that before, and that's coming up really big in the next unit after this, which is called differential equations. But if you can take the derivative of both sides of a problem, you can just as easily take the integral of both sides of a problem. Does that make sense? Okay. Now, how did they get from line 3 to line 4? What did they do? Look at the problem, either on your paper or on the screen. What did they do?
It cancels out because you take in the integral of the derivative.
Oh, did they just switch it? They just switched the dy with the U times dv?
Yeah, aren't these three terms the same as the three above? You see that? They just rearranged the problem, didn't they? Okay, now the whole point is to get the problem isolating u dv, and you'll see later why we do that. So we now have u dv equals the integral of dy minus the integral of v times du. Okay? Now, how did they go from this line to the next line? What did they do?
They took the integral of the derivative, so it cancels out.
They didn't really take the, yeah, they did. They took the integral of the derivative, which cancels out and gives you y. The integral of just a dy, or the antiderivative of dy, is just y. Okay? And so then y on the last line turns into u times v, because up there in the top, that's what y is defined to be. So this is the integration by parts formula. Come over here and put a big star next to this. This is a formula you're going to have to learn, and we will put it in a flip chart at a later date. Now, a few years ago, I was introduced to a video that was put together by some students, It was a project that they did at the end of their AP Calculus course, and it was based on the Star Wars first movie, the one that just, not the one that just came out, but the one before that. And it's really well done. I will show it to you at the end of the year. That's one of the things I do, is I have a couple videos I'm going to show you. But one of the things that they had in this video, which I thought was really good, was a way to remember this formula, okay? So, take a look at the right-hand side. When you see the letters UV, what do you think of in the real world, UV?
Rays. UV light.
UV light. What does UV stand for?
Ultraviolet.
Ultraviolet. So write that down, ultraviolet. So, UV stands for ultraviolet. And then what's inside the integral, V to U, if you kind of run it all together, it kind of sounds like voodoo. So, we're going to call this method ultraviolet voodoo to help you remember the order of the letters. Ultraviolet voodoo. Okay, but you have to remember that it's subtraction and the voodoo goes in an integral. V to U, voodoo. Okay? So, what we have here, look at the left-hand side of this problem. We're dealing with problems where we're integrating. We've seen U du before, haven't we? We've seen U du. That's an easy one. But what we have here is U and dv, which means most of the time we have a product of a function and the derivative of something else. Let me say that again. We have here a function u and the derivative of a different function v. So what we have to do is figure out how to undo that product so we can get what the antiderivative is going to be. Okay? So we are going to create this chart over here. This chart right here, u and du, we've done that before, yes? But we're going to add another column. But I'm going to change the way we do this. It's really going to be dv on top and v on the bottom. And you'll see why later. But u and du and dv and v. That means the left-hand one you take the derivative as you go down. On this one you take the antiderivative. Okay? Because everything in the integral is going to go in the top two lines. Everything in the integral is going to go into the top two lines as we do this. Okay? So, just like when we did chain rule, I taught you some ways to know what u was. Who remembers when we did u substitution? How do you know what u is? The inner function, yes. Or if you have a fraction, which one is it? It's the denominator, okay? So we're going to have rules like that to know which one to stick in the u slot and which one to stick in the dv slot. Occasionally it doesn't matter, but most of the time it does. Because if you put it in the wrong way, it's going to turn the problem worse than it was to start with, okay? So, this is the way the chart looks. If you turn to the back of this page, you will see here are a couple of examples that are worked out. And they go through all of the steps. I would personally rather work them myself. So I will show you on the next page how to do this. So we're going to skip these two right here and go to the top of the second page. Okay. So this talks about how to choose u and dv. Let me scoot it down just a little bit. And this is very important. In choosing u and dv, follow this guideline. The u should be an expression that when you take its derivative, it gets easier. Okay? Or at least not any more complicated. The dv should be something that you know how to take the integral of. Okay? Now, when I was in school, we just had to guess. We just guessed and put things in the different slots and try to figure out which one was which. But now they've come up with an acronym. And that acronym is, how would you say that? LIATE. Or LIATE. Okay? Now, those letters each stand for a type of function. When you're looking for u, you look in your integral for these in sequence. If you have one of these functions in your integral, that's your u. So look at this integral right here. Do I have a logarithm in this integral? Yes, so it's u. Okay? Look at number 5. Do I have a log? No. Do I have an inverse trig function? Do you see, I have a trig function, but does it say inverse on it? No, so it's a no. Algebraic, underneath algebraic, write a letter x and put it in a parentheses. So if you have x to any power, that's the algebraic. So does this have a plain x in it, or an x to a power? Yes, it does, so that's going to be u. Do you see how I'm doing this? You go down the list and figure out, if you have it, stop there, that's your u. Now, first period came up with an acronym to help you remember it, like PEMDAS helps you remember. Please excuse my dear Aunt Sally. I'm going to come out to the side. Let me see here, just a second. I got to have room to write this down. I'm going to do it at the bottom. So go to the bottom of the page and write down Liate. And this is basically, I would call it the calculus prayer, okay? And it stands for let integrals always turn easy. Let's integrals. Now, because what this procedure will do was take a difficult integral and turns it into an easy integral. Let integrals always turn easy.
Wow.
That thought was pretty clever, because that's what we're doing. We're taking an integral that's difficult and turning it into an integral that's easy. Okay? So there it is. Liate. So, let's go back to number 3. Number 3 says, find the integral of x squared ln of x dx. Your homework paper is going to have problems on it that don't require this method. They're the old-fashioned u sub. Okay? U sub, you know, is you're going to have an inner and outer, or you're going to have one that's the derivative of the other. Okay? So what you do is you look at the problem and ask yourself, is the derivative of x squared ln of x? No. It sounds like a silly question, but that's what you have to ask yourself. Is the derivative of the first function the second function? No. Is the derivative of the second function the first function? No. So this is a situation where we need integration by parts, because they have nothing in common with each other. It's not a u and du. It's a u and a dv. So what we're going to do is come out to the side and write u equals and du equals, just like we used to. Okay? And then move over and put dv equals and v equals in that order. dv and then v. Now, first period said I went a little too fast on this first example, so I'm going to slow it down. Okay? Now, based on my Liate, which one of those things should be u? The ln should, because that's the first thing on the list. So in the u slot, put ln of x. So if that's what u is, everything else is dv. So over at dv, write down what you didn't just now write down. That's x squared dx. Okay, so the top line should be everything inside the integral. Everything. Are you with me so far? Okay, now we need to do the math to go to the second line. So if u is ln of x, what is du? This is 1 over x dx. Make sure you put the dx on it. This is where it's important. Du is 1 over x dx. Okay, if dv, if the derivative of a function v is x squared, what is its antiderivative? 1/3 x to the third, not a dx. Now usually we put plus c. I know that. The plus c comes later. So we're going to just put it on the back burner and we're going to come back to it a little bit later. So do you understand where all that stuff came from? Yes, ma'am?
So du is the derivative and v is the antiderivative?
Yes. So down the u column you're taking derivatives. Down the v column you're taking antiderivatives. Okay? Are we good with that? All right. Now we're going to use our little saying, ultraviolet voodoo, to write down what this is going to be. So this is going to equal, and I'm going to write it above it, u v minus integral v du. Ultraviolet voodoo. Okay, so u is ln of x, v is 1/3 x to the third, sorry I'm writing so small, minus the integral of v 1/3 x to the third times du 1 over x dx. So all I did was just plug everything in to ultraviolet voodoo. ln of x times 1/3 x to the third minus the integral of 1/3 x to the third times 1 over x dx. Okay? Like I told you, the acronym, let integrals always turn easy. I have just now created, you may not know it yet, but I have just now created an integral that is much easier than the one I started with, that I can actually do. Okay? So what we're going to do now is we're going to clean that integral up, so hopefully you can see what to do with it. So, in this case, usually we put anything with polynomial stuff, x's to powers, usually goes in front of ln's. So let's just rearrange these. Let's do 1/3 x to the third ln of x. That's just usually the order that it's written. Okay? Minus, I'm going to go ahead and pull that 1/3 out of the integral. And what does the rest of it clean up to be? Just x squared, right? X to the third times 1 over x is x squared dx. Now, isn't that integral much easier than the one I started with? Oh yeah, I can do that one without any sort of u sub or anything. So now we finish the problem. 1/3 x to the third ln of x minus 1/3. Now be careful. What does x change to when I take its antiderivative? To the x to the what? This is x squared, so this is going to go up to the third, which means that what goes into parentheses? 1/3, and second 1/3. The 1/3 that was already there doesn't count. We've got to put another one. Plus c. Now we're ready for plus c. Once you're done pulling everything out of the integrals, then the plus c goes on. Okay? So I'm going to take this one more step because I can combine those together. So it's 1/3 x to the third ln of x minus 1/9 x to the third plus c. And that's my answer. What?
X cubes, like, why can't those like subtract out?
Talk to me. Say what you said one more time.
Like in the answer, the X cube.
I could factor them out. Yes, I could. You don't have to, but you can. So like on a multiple choice problem, they may have those factored out. You just have to know, oh, I could do that. But you don't have to do it. Okay? Good question. Any other questions at this point? Okay, let's do another one. I'm going to do the one on the right-hand side because it's a little bit different. And I'm going to do it in a different color so that the problems don't mesh together very much. Okay? Now, going back to number 3, how many x's do you see in this problem? No, not counting dx. There's 2. There's x squared and there's ln of x. 2. A product of functions. But number 4 doesn't look like that. Number 4 only has one problem, ln of x. But what is the derivative of ln of x? 1 over x. Do you see a 1 over x in here that I can use as a du? No. And I can't just throw it in there. So this is another udv that we're going to use the integration by parts on. So we're going to come up here, u equals du equals dv equals v equals. I'm using a different color just so that I can tell my two problems apart. Okay? Based on our acronym, LIATE, however you want to say it. I don't want to say it latte because then you'll say L-A-T-T-E. No, it's not latte.
I like latte.
Latte's good.
The I is silent.
Okay. What is u?
ln
ln of x. It's the first thing we see. Which means that dv is what? What's left? 1 dx. Exactly. It's 1 dx. That's all that's left. Okay? Now the next step is to do line 2. What is du?
1
Over x dx. We just did that one a minute ago. Now be careful. V is equal to x. V is equal to x. The antiderivative of 1 dx is an x. Okay? So what do you think? So far so good? All right, time to plug it into ultraviolet voodoo. So ultraviolet, so ln of x times x minus integral voodoo. So VOO is the V times, which is x, times 1 over x dx. Ultraviolet voodoo. Ultraviolet voodoo. If you want to write it down, you don't have to. This one's a lot shorter than the last one. Okay. When I multiply u and v, is that ln of x the quantity squared? Is that ln of x squared? No. So I should write it this way. X ln of x. Go ahead and swap them. That's to keep you from thinking that it is. Minus, what does the integral here clean up to be? 1 dx. Can I integrate a 1? Oh yeah. So now we have x ln of x minus just x, and now we put the c on, plus c. So, how do you feel about that one?
It was not as bad as it was.
It's not as bad as the first one. You're starting to get the hang of it. Feeling okay? Questions? Anybody? All right, let's move on. Look at number 5. Number 5 says sometimes you need to use integration by parts as your primary method. So the first thing we do is integration by parts, but then a u sub is needed for the second part. So they're kind of giving you a hint as to what's coming. All right, so let's practice again. We're going to find the antiderivative of this. Now one more time. Do you know the derivative of secant squared? Or the derivative of secant?
Tangent.
It's secant and tangent. Do you see any extra secants and tangents in here? No. And the derivative of just an x is 1. And that leaves this extra secant squared. So this is definitely integration by parts. So u equals du equals dv equals v equals. Okay, let's go down the list. L-I-A-T-E. L is logs. Do you see logs in that problem? No. Inverse trig.
No.
Do you see inverse trig?
No.
No, I see regular trig. That's the T. Okay? So L, no L's, no I's. A is algebra. Do you see any X's in here? Yes. So that's your U. U is X.
Oh, so it's only singular as
X or either singular X or X to any power.
so it can be attached like a function.
No. It has to be like a polynomial. So that means dv is secant squared x dx. Are we good with that? Okay. You fill in the next line. You fill in the next line right now.
Don't confuse me, Alicia.
Okay. So if if u is x, what is du? 1 dx. So I'm just going to write dx. You can put 1 dx. You don't have to leave it off. Okay. If dv is secant squared, what is v?
Tangent.
Tangent. Very good. Tangent of x. Okay. Now it's time for what? Ultraviolet voodoo. You need to remember that. Ultraviolet voodoo. So ultraviolet. So that's x tan x. That's ultraviolet. UV. Some people like to draw arrows because this is the way it goes. UV, VDU. Okay. Minus integral. You got to remember minus integral. VDU. So tan x dx. Are we all in agreement so far? Okay, now. So I'm down to a function that has only one x in it. That's better. Okay, but do you know the antiderivative of tangent? Let's go back to our little list here. Do any of these integrals say tangent in them alone? No, none of them do. So we're going to have to do this a different way, but there is an easy way to do it. Before Christmas, we took a quiz on integrals. And there was a question on there I said is a little tricky, and I was going to give you bonus points if you figured it out. And this is that question.
Oh, it's cosine. No, sine over cosine.
It's sine over cosine. And then you can do a u substitution. So that's what we're going to do. Very good. So this is x tan x minus the integral of sine of x over cosine of x dx. Now you may be thinking to yourself, Miss Bell, you just got rid of an x and now you gave it another one. But it's okay because one is u and the other one is du. So now we have to do a regular u sub, just like before. Okay, so we're going to come out to the side. This is just plain u du only. Which one is u?
Cosine.
Cosine has to be u. Because why?
It's on the bottom.
It's on the bottom of the fraction. Very good. So what is du? Careful. Negative sine of x dx. And I have all of that except for the negative. So now I'm going to change colors. I'm going to give this thing a negative,
So that becomes positive.
which means that the sign outside the integral becomes a positive. Very good. I'm going to circle my du, just like we used to do.
My legs hurt.
Okay. So now we're switching to u's, but this x tan x is already done. So I'm going to write in my u color, but I'm still going to write that down. It's not changing at all because it's finished. Plus integral. My circle is du. What is everything else? 1 over, not cosine, 1 over u, right?
Oh, so it's
So what is this going to be? It's going to be ln. Do y'all agree? Okay, so this is x tan x plus ln. Don't forget the what?
U.
Absolute value of u plus c. But that is not finished because it's got x's and u's in the same line. It needs to be all the same variable.
So you
So-
put in your U.
So I'm going to change the u back. So x tan x plus ln of the absolute value of cosine of x plus c. And now I'm done. That doesn't happen all the time, but it happens occasionally. All right? We're not going to do number 6. And we're actually going to not do 7 and 8 because there is a different method to do it. Please write these words right here, tabular method. Later in this lesson, I'm going to teach you how to do this. And I'll explain what the tabular method is so you can come back and do these if you want to practice on them in order to understand what's going on. DJ, question?
Okay, so you said the cosine had to be u because it was on the bottom?
Yes.
Okay.
When we did u sub, that was one of the things we said. If we're ever given a fraction where nobody's inside, the bottom has to be your u because du can never be on the bottom. Okay? Okay, now let's go to the back of this page and do the last types of problems that we need to look at. Now these are a little bit obscure. Obscure, I need to show them to you, but you won't see them very often. It says sometimes repeated integration by parts doesn't appear to work because you're not seeming to get anywhere. Every time you build your last integral, it's just as difficult as the one before it. So these are what I call looping problems. looping problems. Now, looping problems are problems that when you take the derivative over and over, or you take the antiderivative over and over, you oftentimes end up back where you started. So tell me a function that you know that if you take the derivative, you're going to end up right back where you started.
E raised to the x.
E to the x. So e to the x is a looping function. Taking its derivative over and over and over is not going to help. It's not going to make it less complicated. Now, can you think of another one? It takes a double derivative before you get back to where you started. Sine or cosine. So those are the three that tend to do this. So if you see two of those in a problem, you're going to have a situation where you're having a looping problem. Okay? You're just never going to get anywhere. So there's a special way to do these problems. We're only going to do number 9. So let's talk about how to do this problem and how to get rid of the looping issue. So we have our u and our du and our dv and our v. Now, based on our acronym on the previous page, LIATE, logarithms? Nope. Inverse trig? Nope. Algebra. You see algebra up there? No. Trig. Yes. So trig is our fourth choice, so that means that sine of x is u, and that means that dv is the rest of it, e to the x dx. Now, honestly, looping problems tend to do to where it doesn't matter which one is u and which one is dv. But I just always do the same, go through the list and go that way. Because the first time I did this, I put u as e to the x, and it still worked. Because they loop. Okay? So what is du for sine? Cosine of x, dx. And what is v for this? E to the x. Okay, so we're done there. Now, this is the one problem where you need to copy the problem on the left. You have to copy the problem or it's not going to work in the end. E to the x sine of x equals.
Wait,
Yes.
so how do we know? Is it going to tell us when it's going to be a looping problem?
No, you've got to be on the lookout for e's, sines, and cosines. So if there's two of those three in the problem, you got to do the looping problem. Okay? So uv sine of x times e to the x minus voodoo e to the x cosine of x dx. Okay? So we did our ultraviolet voodoo. And our integral at the end is no better than it was when we started, is it? It's still got two looping equations, and that's okay. So what that means is we got to do it again. We've got to do the u dv thing again. So u equals, du equals, dv equals, and v equals. Using the same procedure, the trig function is u, the dv is e to the x, just like before. So this time, though, u is cosine, and the dv is still e to the x, because it didn't change. So what is du this time? Negative sine of x, dx, and v is still e to the x. Okay? So we recopy the problem equals. Now usually these are written in the reverse order like they are in the integral. So I'm going to go ahead and flip them around. E to the x sine of x, then a minus, then a parentheses. Now I'm going to pretend the only thing on the page is that integral right there. And I'm going to do ultraviolet voodoo to that. Okay, so uv cosine of x times e to the x minus the integral of voodoo. E to the x times negative sine of x. Make sure you put the negative sign into parentheses. Dx and close it. Okay? So let's clean this up a little bit. So integral e to the x sine of x dx equals e to the x sine of x. Now we've got to distribute these negatives here. So it's minus e to the x cosine of x, switching those two around. Now look very carefully. What is the sign going to be in front of the integral on the end? How many negative signs do you see?
It's negative.
It's going to be negative if you pull this one out. Are you with me? So a negative times a negative is a positive, but you pull that one out, it turns it negative again. So minus integral e to the x sine of x dx. Okay, if I say the phrase right back where I started, do you know what I'm referring to here?
The problem you were given.
Yes. This matches this. Do you see that? Okay? So what that means is I can actually, this is a number once it's evaluated, I can move this to the other side and add it to the other one. Just like if it was an X or a T or a Y or anything else. So if I move this over here and add it to the one that's there, how many integrals am I going to have? I'm going to have two of them. So the left side is now going to say 2 integrals of e to the x sine of x, because this one is negative. When it moves over, it's going to turn positive, equals e to the x sine of x minus e to the x cosine of x. That's what looping problems do. You end up back where you started, eventually. So, since I'm solving for the integral, I want to know what that equals. I need to get rid of the 2. How do I get the 2 off of there? Divide by 2. That's what I'm going to do. So that means that integral of e to the x sine of x equals e to the x sine of x minus e to the x cosine of x all over 2. But I forgot something. Plus e.
Is it over?
Huh? Is it over? Yes. Did I solve for the integral that I was looking for? Yes. That's when I know I'm done. Because that integral is by itself. And there's no other integrals in the problem. Then I'm done. Like I said, this is rather obscure, but you needed to be exposed to it.
But are we gonna like have these tests on like a test or something?
Very rarely.
I'm talking about your test.
Oh, I don't know. We'll see.
Let's say no.
Let's say no.
What about the homework?
There might be one in the homework. I don't know.
No. You threw my pen on the ground.
Okay.
That was really
Questions? All right. Now we're going to talk about what's called the tabular method. Okay. The tabular method is nice because you don't even use ultraviolet voodoo at all. You just put all the information into this array, you pull out the pertinent stuff, and you're done. It's just, it does that repeated UDU stuff for you. Okay? Now, notice the functions that are in here. The tabular method works with e's, sine, cosine, and x's. If you have any of the combination of those, usually it's an x with one of the other 3. That's when you know to do the table. If you have an x and an e in the same problem, or an x and a cosine in the same problem, or an x and a sine in the same problem, that's when you do the table. I'm going to jump back to the top and write down for the looping problems, it's e, sine, and cosine only. Okay? So these weird ones that we just did have e's, sines, and cosines only in the integral. This one has e's, sines, and cosines along with an x. Yes?
So like, what if there's an E and a sine, but they both have E and sine? So how do you know if it's going to be tabular or looping?
Okay. Tabular will always have an x in it. It'll be
Like a
x with one of the
singular?
other three. It'll be x and e, x and sine, or x and cosine.
Okay.
That's what I'm saying. With x's. So x with cosine, x with sine, or x with e. Those are the only three choices. Okay? So, the procedure tells us we create three columns. We call them sines, u, and dv. So over here, we're going to write sines, u, and dv. And this is going to be the majority of the workspace except for the final answer. Okay? So when we know we have to do the table method, we're going to put sines, u, and dv. Now, we are going to alternate signs down the sign column, and we always start with plus. So it's going to go at least plus, minus, plus, minus. Sometimes it goes farther than that. Okay? How far do you go? As far as it takes your u to get to 0. Okay? Here's what I mean. The u is always the x function. So in this case, it's x squared. So wherever the x alone is, that's your u. Because that is the one, if you take its derivative over and over, it's eventually going to get to 0. Does that make sense? Think about taking the derivative of x squared in your head. Over, and then over, and over. It doesn't loop, it goes to 0. Okay? dv is what's left. Cosine 3x, and we drop the dx off the table. We drop the dx off the table. Okay. Now, down the u column, I want you to take the derivative over and over and over. Okay, so what's the derivative of x squared? 2x. Line it up with the minus sign. What's the derivative of 2x? 2. What's the derivative of 2?
0.
As soon as you hit 0, stop. That's when you know to stop. As soon as you hit 0, stop. Okay? Yes.
I'll use the restroom.
Go. Okay. Now, for the dv column, we're doing antiderivatives, just like we did in the chart. We're going to go backwards. Take antiderivatives, and then take the antiderivative again, and the antiderivative again. Okay. What is the antiderivative of cosine? Sine 3x. Now we're going to do a little bit of thinking here. Because in reality, this is a chain rule problem. U is the inner function. So what number has to be in the front here so that when I take the derivative, there's no 3 in front of it? Not 3.
1/3.
1/3. Very good. This one needs a 1/3 there. Okay? Do I need to show you why? Yes. Okay. I did this last period. I'll do it again. Okay. I'm going to do this out to the side. So I'm integrating cosine of 3x dx. Agreed? What is u?
3.
The inner function 3x. du would be what? 3 dx. So that means I need a 3 right there, right? Which means I need a what outside? 1/3. That's the 1/3. That's the 1/3. Okay? Are you with me?
Yeah.
Okay. So, keeping that in mind, every time we go back, we got to throw a 1/3 outside. So what's the antiderivative of sine? Negative cosine. So we're going to need a negative, leave some space for the fraction, cosine of 3x, but what fraction's in front now? 1/9. Very good. Okay? Do it again, because you got to line up with the 0. What's the antiderivative of negative cosine?
Negative sine.
Negative, oops, I forgot to leave room for my fraction. There's my fraction bar. Negative sine of 3x. 1/27, and I'm definitely going to have to use this video because I did it wrong in the other one. I put positive 1/27. That was my mistake. Okay, so how do you do this? The sine connects to its u, but you don't do the 0, because 0 times anything else is 0. Connect the top 3, and then connect down 1 level the u with the dv. You connect straight across on the sines and down 1 level on the u and dv. Okay? what you will do is now multiply all three of the things connected together and write it down. Then go to the next line, do it again, write it down until you run out of lines and you're done. That is the antiderivative of this problem. That's the answer. Equals. So watch this. I have a positive x squared times 1/3 the sine of 3x. So let's write all that together. So that would be 1/3 x squared sine 3x. Doesn't matter how you put them in order. Usually constants come first, x's come second, trig comes third. That's just the way it's usually written. Okay? Now look at the next three. What sign will it be? It's a negative times a negative 1/9, right? So it's positive. So plus, combine the constants, that's going to be 2/9 x cosine 3x. Are you with that? Okay, now the next line. So a positive times a negative is a negative. And then combine the constants, 2/27 sine 3x. Tack on a plus c and you're done. That's the answer. Yuck. It's right, but it's yucky, but it's right. That's what I was trying to say.
I like it.
Okay? All right. Let's do one more. Let's do number 12. Now, do you see that this is going to be a table because one is an x and one is an e? X with e, x with sine, x with cosine. That's how you know. So we're going to do the table. We're going to do sine u dv. 3 columns. Remember that the sine column goes plus, minus, plus, minus. Usually you have to go at least 4 lines. Sometimes you go more. In this case, what goes in the u column? X to the third. And what is left? E to the negative 2x dx. We'll just leave the dx off, remember? Okay. Now what do we do with x to the third?
Take the derivative.
Take the derivative over and over until we get to 0. So x to the third becomes what? 3x squared. What's 6x, 6, and then 0. So we got to put a plus sign. Make sure we have enough signs of S-I-G and S across the bottom. Okay? Now think carefully going the other way. What's the antiderivative of an e? What's copy paste? Okay, that's the derivative method. It's copy paste times the derivative of the exponent. But in this case, we're doing the antiderivative. So that means we need to put a number in the front, kind of like we did that 1/3. It's going to be in, careful, negative 1/2. Negative 1/2 in the front. It's the same process like we did with the u substitution. U would be negative 2x, du would be negative 2, so we got to throw a negative 1/2 outside. Okay. So let's do the next level. Copy paste again. What number goes in front? Careful. Positive 1/4. Do y'all see why it's positive?
Yeah.
Because it's bringing down another negative 1/2. And then next line is copy paste again. Negative 1/8. And finally copy paste one last time. 1/16. Okay? All right, let's connect them. So straight across on the signs, but not the 0, down on the u's to dv's. So this will be negative 1/2 x cubed e to the negative 2x. Agreed? What sign will the next line be? It's a negative times a positive 3 times a positive 1/4, so it's negative 3/4 x squared e to the negative 2x.
Can we write it on 2 lines?
Sure. So the next one's going to be a negative 6 over 8, you do not have to reduce that. So I'm going to leave it. X e to the negative 2x. And then the last one is going to be negative again. 6/16 e to the negative 2x. And we're done. Oops, no we're not.
Plus C.
Plus c. The spell almost forgot.